Okay, your screen sharing, there we are. Let's go back. Right, okay. So the challenges of vertebrate flight, and I'm not talking here, I'm talking specifically about vertebrates, and in fact, I'll be talking largely about birds and pterosaurs. I'm afraid, bats will also fly, but I don't have time to cover them. So let's start with what actually is flight. Would you excuse me just one moment? I've got something, I can't see my slides properly because that's better. Sorry, I just got the thumbnails out of the way. I couldn't see my slides because there's lots of pictures of people. So what is flight? We talk about the challenges of vertebrate flight, and we all think we know what we mean, and we probably do, but let's think about some definitions. Flight can be considered as a motion that resists the force of gravity, but importantly, it's a motion that has a horizontal component. When something is flying through the air, it has air resistance, drag, and you could say, well, that resists gravity. But lift is a process that provides a horizontal component. So, here we go. So, for example, this little creature is not flying. It's leapt out of a tree, and the only thing that's slowing it down is the aerodynamic drag past its body. So I would not regard that one as flying, that's jumping. This one, however, which has evolved patches of skin between its limbs, is flying. So it's generating a vertical force, a drag force, but also those membranes are generating a lift force, which means that instead of just dropping vertically, that little creature has some horizontal travel. It's not a very efficient flyer, but I would definitely say that that creature is flying. How does it work? How does flying work? How does lift work? Well, if you go on the internet, you will see this explanation. It's called the Bernoulli's explanation, or the equal transit theory. So if we start from the left of the picture, you've got a blue blob and a red blob. Those think of as two molecules, if you like, of air. In this case, you've got the air flowing over a fixed wing, but it works just as much the other way around when the wing is moving through the air. Those two blobs move along the red and the blue and the red paths until they touch the leading edge of the wing section, at which point they part company. One of them goes over the top of the wing and the other goes underneath the wing. And this theory says that they must arrive at the trailing edge, the back edge of the wing, at the same time. So because of the the teardrop shaped aerofoil, the blue one has to go further than the red one. So the blue one has to go faster. And there is something which is correct. There's Bernoulli's principle that says as the speed of a moving fluid increases, the pressure within the fluid decreases. So the argument goes that because the blue blobs have to move faster than the red ones, they reduce the pressure, and as such you get a pressure differential across this teardrop shape and you get lift. But that explanation requires that the aerofoil section is some sort of teardrop shape, which then makes you think, well, how do things like this stay in the air? Paper planes don't have teardrop wing sections, and indeed neither do many insects. So this dragonfly, according to that theory, shouldn't be able to fly, but it clearly does. And interestingly, back in the 30s, a German guy called Anton Flettner built a ship which crossed the Atlantic with these rotating cylinders. So even a cylindrical shape can generate lift. I mean, they have to rotate in order to do that, but they generate lift. And you can see here the flow patterns. On the left, you've got the rotors when they're fixed and the flow just goes round them, equally either side. But if you start rotating that rotor, you see that the streamlines, that the flow patterns change, and they cram over the top of the cylinder there, and that shows you that the pressure is reducing on that side. So what you've actually got is a process of what's called circulation going on, and that's what's actually generating the lift. And Bernoulli is applying because the velocity is greater on one side than the other. But it's actually much greater than the difference is much greater than you would get from the so-called equal transit theory. Another thing to notice there is that whereas on the left, the incoming flow is horizontal, on the right, it's actually being affected in front of to the left of the rotor. So it's a big field here, a pressure field going on. It's not just restricted to immediately around the rotor. And the flow is what's called upwash. The flow is coming up to the rotor and then also going down. So there's downwash. So it's creating a whole wide field rotation. And what that means, to cut a long story short, is that a flat plate is perfectly capable of generating lift. It's not perhaps as efficient at doing so as a teardrop shape under certain circumstances anyway, but it can generate the pressure differentials that you need in order to fly. So you don't have to have some fancy aerofoil shape in order to fly. But it helps, it does help. And the other important thing relevant to this talk is the curvature of the aerofoil. I've just been drawing more or less symmetrical aerofoils, but if you increase the curvature of the cross-section of the aerofoil, what's called the camber in aerodynamic terms, you increase the maximum lift that aerofoil can produce. Don't worry about the terminology here, but just look at the way those curves get higher, which is a proxy for generating more lift. So if you want to generate a higher amount of lift for a given area, you need to have a cambered aerofoil, and we'll see why that's important later on. So that's really about how lift works and how it gets you into the air, or keeps you into the air. But if you're going to go very far, you actually have to have powered flight. I mean, gliding's fine, and birds and pterosaurs probably make great use of it. But ultimately, at long distance, you've got to be able to have some power. So aerodynamicists obviously have for a long, long time been able to calculate the power requirements of flying bodies, of aircraft. And to simplify it dramatically, there are two separate components to the power. One is the power due to the parasitic drag. That's the drag the body experiences as it passes through the air, or indeed in water. Things can fly underwater. And that parasitic drag starts at 0 and increases, in fact, as the cube of the speed. So it's a curve which increases rapidly with speed. So that's the airflow over the body and the wake and all the other stuff that goes with pushing it through the air. However, it's also generating lift, and lift doesn't come free. Lift has a drag penalty associated with it. It's called induced drag. We don't have time to go into it today, but it's all to do with that vorticity I showed you earlier, that vortices can't exist in isolation. So actually the tips of wings shed vortices, and they're wasted energy. There's nothing you can do about that. That's basic physics. You can reduce it, and there's, I think, ways of reducing it, but ultimately it's still there. Now, the important thing about induced drag is that it has this shape. It is very high at low speeds and then decreases as speed increases. This is well known, and of course it applies to aircraft. When you add those two together, you get this characteristic sort of U or J-shaped power curve. So lots of power needed at low speeds, and then once you get up to a higher speed, the power requirement actually drops, which is sort of counterintuitive, but that's how it is. And then, because the parasitic drag is going up, as you go faster still, the total drag, or the total power requirement, does increase. But if you think about over to the left there, you know, if you're coming, when you're flying in an aircraft and it's coming into land, suddenly it gets really noisy and the engines are working really hard. That's because it's flying slowly. They have to land at about 150 knots, whereas they cruise at 600. So suddenly they're to the left of that curve and having to generate, the engines are generating a lot more power than they were when you were crossing the Atlantic or whatever. Well, it's not theory, this is fact, this is reality. And this reality has been measured in birds. So it does apply to the natural world as well. This graph is the vertical scale is the power, the muscle power, in fact, and the horizontal one is the flight velocity. And if you look, say, at the magpie, I've had an extreme example there. If it's flying at 6 meters a second or so, it's using about a third of the power that it needs at 0 to take off. So the cockatiel is similar. The dove seems to be rather better at doing that. But the J-shaped, U-shaped curve definitely applies, and there's a big difference between the power you need to take off and to sustain very low speed flight, and the power you need to go fast. And incidentally, that's why very few birds can hover, because it needs so much power, and there's adverse scaling effects, which mean as you get bigger, it gets increasingly difficult to hover. So, given that background of the aerodynamics, how has nature evolved different morphologies to deal with it and to be capable of flight? Well, there are three really fundamentally different morphologies. There's that of the pterosaur, which is at the top there, or in the middle of the three diagrams on the right. They're all vertebrates, so their basic skeletal morphology, of course, is familiar and similar. But what the pterosaur has done is it has a membrane wing which is attached to a single hyperextended finger. So it's like a sail, if you like, with a single slender mast. And then behind that there is a membrane. Birds, on the other hand, of course, use feathers, and these feathers extend the wing beyond the span of the wing bones. And that's how they create the aerofoil surface. And then thirdly, there's bats, which are a little bit similar to pterosaurs in some ways. Of course, they use a membrane wing, but they're different in that they support their membrane wing on their complete hand. So all the fingers are used to support the membrane. So that's a different solution to the one that the pterosaurs adopted. Incidentally, I mean, it's a bit of an aside, but it's worth remembering that in case of birds, feathers are exapted. We know that the dinosaur antecedents of birds had feathers, which they didn't use for flying. Maybe they used them for display, as this suggests, thermoregulation. There's all sorts of possible reasons why they had feathers, but they certainly weren't originally there for flight. So there's huge debate amongst scientists about the evolution of flight and how creatures got into the air. Taking it very, very simply, there are two competing views about how bird flight evolved. One is the so-called trees down theory, and the other is the ground up theory. The trees down theory suggests that these proto-birds climbed up in trees and leapt out of them. And of course, if you think back to our J-shaped curve, that's great, because when you leap out of the tree, gravity accelerates you, and assuming you don't hit the ground before you build up speed, you've immediately let gravity get you to that low point in the curve where you don't need a lot of power in order to fly. So in a sort of parsimonious sense, that's quite a compelling theory, but it doesn't seem to have a lot of support these days amongst anatomists and others, because as I understand it, they're saying that early dino birds and all the creatures who are experimenting with flight, they probably weren't very good at climbing into trees. So the idea that they could climb up to a high point and leap out morphologically is questioned. I mean, I'm not into that debate, so there may be those in the audience amongst you who know it better than I do, but that, I believe, is one of the arguments. So if the proto-birds were not climbing up into trees and or up into cliffs and leaping out, how did they get into the air? Well, they got into the air from the ground up. And of course, that, as we can see from the J-shaped curve, is a challenge, because you've got to provide a huge amount of power. And that's really a lot of what this talk is now about, is the challenge of that J-shaped curve. Here it is again. This is a theoretical calculation by Jeremy Rayner, who back in the 70s, 80s, 90s even did some really fundamental and extraordinary groundbreaking work on the mathematics of animal flight. I mean, he is the expert on the subject, really. And this shows the calculated flight power for a pigeon against velocity. And this is at a 90-degree stroke angle. So in other words, the wings are going up and down 45 degrees. And you can see in that case, there's a very large difference between the minimum at around 6 meters a second and the 0 foot forward speed power requirement. However, his calculations also showed that if you change your stroke angle and make it to 180, so in other words, you bring your wings right up above your head and then down, you can reduce the amount of power you need at low speeds. You increase it at high speeds, which is why when you look at, if you actually observe birds, you will see that when they're flying slowly, they're using a very deep stroke. But once they get faster, they automatically, and probably without really realizing it, change over to a much more shallow stroke angle. And indeed, at high speeds, they're probably even less than 90 degrees. But the point here is that in order to minimize the power requirement at low speeds, you need this very, very extreme stroke angle. And with that stroke angle goes the requirement to actually rotate, pronate and supinate the wing. Because if you just flap it up and down at those very large angles, all it does is stir the air up. You just get drag, you don't get any lift. So you actually have to rotate it so the pitch angle, the angle of attack of the aerofoils is correct. So in order to make the wings work at those low speeds, there are some very complex kinematics required in the joints and everything else. Whereas if you are flying faster, you'd have a much reduced stroke and actually a much less of a requirement for pitch. So you need a much, much simpler kinematics, which is perhaps another argument for the trees down theory, because if you leap out of a tree, you can just put your wings out, pick up speed gliding, and then immediately go into the high speed simple flapping. So another argument for that. But if we're looking at the ground up theory, then there's no doubt that you've got, in order for it to work, in a sense, you've got to have these deep strokes and complicated flight kinematics. So how do birds get around that, or how do they reduce the negative side of that? Well, what they do actually when they take off is they don't just stand and flap. They use their legs. And this is some groundbreaking work that was done by Earls in 2000. Other people had done similar things before, but she perhaps did it particularly well. She got a variety of little birds to stand on force plates, and they were caused to take off quickly. I don't know what incentives they used, but anyway, these birds were made to take off quickly into the air. And she measured the force they applied. So if again, we start on the left of this graph, you see the vertical scale is the force that the little bird is exerting onto the force plate, which of course initially is one, is its weight. It's the force times weight. So there's one body mass, body weight of force there. So you go across, the line goes across initially till you get to point 0, at which point the bird has decided it's going to take off. It crouches down, and as it does, it actually slightly reduces the force on the plate, and then it pushes really hard with its limbs and creates a launch impulse which gets it into the air. And you can see from the little graphics above, which are linked to the positions along there, that the wings are not doing very much. The wings are up in the air as the bird is coming off the ground. So the wings are not doing much at all in the initial stages. Once it leaves the ground, then the wings start to take over, and that's where the deep stroke and the complex kinematics comes in. But the bird, through using its legs, has at least given it some initial velocity, so it's avoided that extreme peak drag or power requirement at very, very low speeds, and then it's up and away. And you can see in that case, this is a little not a ground dwelling bird, which uses flight for escape. It actually is producing a force of 8 times its body weight as it pushes off. That's extreme. A lot of birds, it's more like 4, but they produce a significant force to get them up into the air. And in order to do that, they, as I say, they have to have this complex kinematics. I can't really go into it all here, but many birds use a process called tip reversal, which is where the wing tip reverses on the upstroke, because obviously you've got to get the wing up in the air in order to push down and generate the lift. So that's one way of doing it. The other way is what's called flex wing. And if this video will work and you watch the blackbirds, the rooks, you'll see how they do it. This is a very slow motion film of them eating in our garden, and you see the wing goes. Look at the one behind. Its wings going up as it's taking off, going down because it's coming up to push the other one off the food. And you see the way the wings fold away. They flex as they go on the upstroke. Some really complex stuff going on there. And then they go on the downstroke again. And that's letting it up. And so that bird has taken off almost vertically. It's used a huge amount of force to do that. The wings flex again. And the other one starts to get the message that it's time to go. And you see there's lots of other things going on there which I haven't got time to go into. But the important message is what's going on is far from simple. It's not just a matter of flapping up and down. So let's just have one final thing on that. This is another rook. It was on a railing on the beach at Sandown, and it's going to show you how it takes off. So there we go. I'm walking towards it and it's beginning to think, time to go, I think. So it crouches down, crouches right the way down, keeping a beady eye on me, and then says, right, I'm going. So it pushes up with its legs, pushes up even more, and look, it's just putting its wings into the air as it's pushing up hard with its legs, wings going up again, and there the wings are only just starting to come down as its claws are leaving the balustrade, and off it goes. See, if you know what you're doing, it's easy. The other aspect which needs a bit of thought is landing. Because again, you're coming in fast, so you're going to break something. And birds, they can't change the camber of their wings, so they can't change the amount of lift that the wings produce in that sense. So what they've done is they've evolved a number of passive systems. And you can see on the egret there on the top right, all across the leading edge of the wing, feathers are popping up. And they are actually, they're from underneath the wing, and they're like flaps really, and they are having the same effect of increasing the camber, which is what aircraft do. As I mentioned, when aircraft come into land, you not only do you hear the engine straining, but you hear all the whirring and grinding of the flaps coming out. And if you look out at the wing, suddenly what was a nice smooth wing has all sorts of bits hanging off it, and these are all to increase the camber of the wing, so that the aircraft can fly more slowly and generate more lift without falling out the sky. And that's what those feathers are doing on that bird. And on the one, this is a heron, I think, on the bottom picture, you see the feathers on the top of the wing are also popping up, and those are also helping to control the flow. It looks messy, but it actually helps control the flow as that bird is coming into land. So that's how birds manage to keep control when they're landing. There's another one there coming in. So against that background of what's involved in getting around in the air, one of the things that I find fascinating is just how big, theoretically at least, flying vertebrates could become. And it's a matter of some discussion amongst people. Fundamental to understanding it is understanding the effect of scaling, so-called isometrics or allometrics. So let's start with a simple cube. Let's assume that that cube is 1 centimeter, 1 centimeter, 1 centimeter sides, and we double it. So we've now got a cube which is 2 by 2 by 2. So it's doubled in linear dimensions, but the area of the faces has actually gone up by a factor of 4 because the area is 2 times 2 and the volume has gone up by a factor of 8. I mean, this is what engineers refer to as the square cube law, and say it's also called isometrics, but it's fundamental scaling. This is nothing peculiar to paleontology, biology, or anything else. This is just physics. This is how things are. And it has all sorts of implications in the human-made world and also in the natural world. So let's think about it this way. Here's a cat, slender legs, long thin tail, and a very good mouser. Now imagine we scaled up this cat hugely and made a cataphant out of it. Not such a good mouser with long slender legs. Well, behavior aside, that creature is impossible because those legs would not be strong enough to take its weight, because the strength of the legs is more or less proportional to the cross-section of the bones, which is an area thing. The weight of the animal is a volume thing. So the volume has gone up by a factor of, well, if it's more than double that, but it's gone up disproportionately compared to the area, which is why elephants don't look like scaled up cats, or mice for that matter. They have much, much more stout legs. They move more slowly and all sorts of other things, but the fundamental physics of the structure is that they have to have much stouter legs in order to be strong enough to bear that extra body weight. And this was put rather eloquently back in 1926 by Haldane on an essay on being the right size. He said, you can drop a mouse down a 1,000-yard mine shaft and, on arriving at the bottom, it gets a slight shock and walks away, provided that the ground is fairly soft. A rat is killed, a man is broken, and a horse splashes. It's a rather graphic effect of what happens with scaling. But if you want a more technical assessment of it, there's a really good paper by Alexander, who did so much fundamental work in biomechanics, body support scaling and allometry. Alexander, 1985. McNeill Alexander is the man, if you like. He did a huge amount on this, and so any of his papers, or many of them, are very relevant to understanding the effects of this on biology. Now, one of the things that you can then do if you apply this isometrics, this scaling laws and things, is look at how power scales. And what you find is that power required, the power available to a flying creature varies as the mass to the power of 5/6. Sorry, I don't have time to justify that now, but that's how it works out. So that's and that's on a log, drawn on a log scale, so it's a straight line. So that's the power available, varying as the mass of the creature to the power of 5/6. However, the power required varies with a different exponent. It varies with the exponent of 7/6. So the power requirement at some point becomes more than the power available for a given morphology. And people have argued that this is a very good way of determining the upper limit for the mass of a flying creature. Because they say, well, if you calculate the power available and the power required, where they cross over is the maximum mass that a flying creature could achieve. Well, I mean, the fundamental theory behind that is undoubtedly correct, and at some point that crossover will occur. The question really is whether it's actually very useful in determining these things. Now, someone called Colin, who was also at Bristol with Jeremy Rayner, they didn't apparently get on too well together, sadly, but Colin did a whole lot of work on bird flight too, and did some extraordinary, particularly the more sort of practical work. He was much more of a practical person than Jeremy Rayner. Anyway, he looked into this and produced this rather busy graph. The vertical scale, don't worry exactly what it means, but the where you get to 1 on that scale is the equivalent to that crossover point there. So what he did was he plotted all sorts of families of birds onto that against body mass. So he calculated this exponent, or this character, which comes out at 1, where you have the crossover for many different birds. And what he said was, or discovered, was that the crossover point occurs at round about 20 kg, which just happens to be round about the maximum size of extant birds. So QED, he argued that he had explained why you don't see any birds much bigger than 20 kilograms. However, no one seemed to have told birds in the past about that. We know from the fossil record, good fossil record, that there was a sort of condor from hell that lived in modern-day Argentina in the Miocene, called Argentavis, and that was about 6 meters wingspan, so twice the size of a modern condor, and probably weighed about 70 kg. Similarly, there was a seabird called Pelagornis sandersi, which was a bit lighter, but probably had a larger wingspan, 6.5 meters or so, 30 kg. Now, to my mind, it stretches credibility to think that those birds would drag those huge wings around if they were flightless. Surely evolution would quickly have reduced those wings down to nothing. And also the feathers on them have various characteristics which imply flight too. So there's all sorts of reasons to believe that those birds were capable of flight, and that therefore there's something wrong with the approach that Pennycook used. And here's my view on what went wrong. His line is a line which in effect represents the average bird, because that data is not measurement scatter, which is what you normally draw a best fit line through. Each of those points, if assuming they're accurate, are real points for real morphologies. So what he should have done is said, okay, well, let's draw a line through one side there, which are the birds which perhaps are not very good at getting big. I mean, they're no doubt very good at what they do, but they're not a good model for getting big. So the largest, if you scaled up one of those, the largest they might be able to get to is about 2 kilograms. However, if you take a morphology which is better able to scale up and get big, you draw another line and you get something there which is in excess of 100. So in other words, if you think that approach I'm using there is credible, then the methodology that Pennycook came up with gives you predicts a mass of somewhere between 2 and 102 kilos as the maximum possible size of a bird, which is not very helpful, is it? I mean, it really doesn't tell us very much. I mean, we know that the physics ultimately must apply, so there must be some upper limit to the size of birds, but nothing had ever approached 100 kilos. So maybe we've not found the fossils, or maybe there's other reasons why they never got that big. But it would appear that if you scaled up some of those birds of the right morphology, they could, in theory, get to that sort of size. But we also know that pterosaurs got bigger than birds. So what is it about pterosaurs that enabled them to get even bigger? Well, let's just look a bit about the evolution of pterosaurs. Of course, they were flying very capably when dinosaurs were still messing about with feathers showing off to each other and discovering that maybe they could generate something called lift and possibly one day get into the air. So pterosaurs have been doing that for a long time while dinosaurs were still just getting the hang of it. And this is a very, very crude phylogenetic assessment of it in the Mesozoic. The wiggly line in the green above is some sort of measure of the diversity of pterosaurs. You see it peaks in the early Cretaceous and drops down. I think more recent work suggests that perhaps that graph is exaggerating that reduction in diversity. Anyway, it's not really relevant to this talk. The blue lines are the two main lineages of pterosaurs, and you can see that deep in the early Triassic is somewhere where they come from. Birds didn't get their act together until, well, birds themselves, until the early Cretaceous. Feathered dinosaurs that were probably capable of some sort of flight were starting to experiment with that in the mid-Jurassic. So pterosaurs had been doing flight for a long while before birds. The actual evolutionary path of pterosaurs is not well understood. There's a paper that came out very recently, which I think, sorry, I haven't got it here, but shed some light on it, but this is a view by Mark Whitten of what might have been a sort of proto-pterosaur. I mean, there's no fossil evidence for that, but Mark is suggesting that some little reptile-y thing started to have membranes around its forelimbs, which of course would have enhanced its ability to travel horizontally, and so give it some lift. Back to our little flying squirrel earlier on. That wouldn't have been flapping, it would have just been able to travel further as it leapt. Then perhaps he speculates that that membrane increased and you ended up with a creature like that with a long tail. What we do know is that the earliest pterosaurs, Rhamphorhynchids they're called, had long tails. They were relatively small, maybe I think up to about a meter, but had all the other characteristics which are fundamental to being pterosaurs, but they had these long tails. And then sometime in the Jurassic, another lineage appeared, the pterodactyloids, which, similar in many ways, but with no tail. Probably therefore aerodynamically more capable, and they certainly were got bigger. It was very common, Pteranodon, things like that, 6-7 meters wingspan was a common size for these big pterodactyloids. And towards the end of the Cretaceous, along came the Azhdarchids, and we ended up with huge Quetzalcoatlus type creatures of this sort of size. I mean, this is another Mark Whitten illustration. Mark knows very well that giant giraffes and Quetzalcoatlus didn't live together, but he put them on the same illustration to make the point that this creature, the Quetzalcoatlus, could have been almost eye to eye with a giraffe. So to stay in the air, they need a wing. So let's look quickly at the wing structure. Here's here's a pterosaur in flight. There's a supporting wing spar along the leading edge, and then the flexible membrane, which we've talked about. A bit more detail, the bones of the creatures are very thin-walled. They're very large diameter, very thin-walled. They vary in thickness as you go round, and they have internal supporting struts, trabeculae. So depending on where you are in the wing, the cross-section can be circular, oval, or even almost triangular. But the very noticeable characteristic is how thin-walled they are, presumably weight-saving requirement, because they were pneumatized. So they're thin-walled and full of air rather than a fluid. And there you can see a big assemblage of bones. I won't try and pick them all out for you, but the important thing to notice is that the wall thickness is very, very thin on those bones. But also that from fossils like that, we have good record of this. We know this for sure, that this is, you can pick that lot out and reassemble a pterosaur from it. So the membrane on the pterosaur, how was it reinforced really. How could it work as a supporting lift? Well, it was reinforced with what are called actinofibrils, which are long fibers, probably made of keratin, like our hair, and they were embedded in the surface of the wing, and that gave it its ability to form an aerofoil shape. And we know that from fossils of small rhamphorhynchids, the one down there on the right. So there is some soft tissue preservation. And that's how the wing builds up. There's a layer of fibers. There's probably, then underneath that you've got muscles and blood vessels, of course, because it's living tissue. One of the issues that people have wrestled with is how you can imagine that membrane being stable. I mean, these are flags, and of course they're not stable, they're fluttering. So what we do on man-made things is we put battens in them. And this is a windsurfer sail, and those horizontal lines are stiffening so that sail doesn't flutter and he can go along at a high speed. But there's absolutely no fossil evidence for battens in or anything remotely like it in pterosaurs. So how did they keep their membrane stable? Well, they did it by the morphology, I think, of the way that it was done. And this is a sail on a jangada, which is a boat used in northeast Brazil. And you can see that membrane is stable because they have tensioned it round the leading edge, which is bamboo, and the trailing edge is hollow. And this is what pterosaurs did, I think. And when you look at in my PhD work, I measured the strength of the wing spar and found, rather to my surprise, that the wing spar is stiffer anterior-posteriorly than dorsoventrally. You might imagine that dorsoventral, where the lift force are, is where all the material would be disposed, but actually it was biased towards the anterior-posterior, which is what you'd expect if you're trying to tension the wing. So it suggests that keeping the membrane under tension in pterosaurs was a big deal, and so on. So how big could pterosaurs get given that background? Well, can they fly? And this was some work I did in my PhD and then reported it later at an SVP meeting. The Asdarchids got huge. Various people have made the mass estimates, some as low as 70 kilos, some as high as 500 kilos. And we know that they got up probably to 10 meters wingspan, certainly. So they did get big. And there's a lot here about the mass estimation. Various people, Don Henderson did it and things like that. But if you go through, the latest views are that Quetzalcoatlus, which is about 10, 11 meters wingspan, probably weighed about a quarter of a ton, 250, 260 kilos. That's a big creature. So what's going on? It had the challenge, like birds we've discussed, of getting into the air. The physics of flight is the same whether you're a pterosaur, airliner, or a bird. And so what I looked at was how it could get into the air. Once it's up there, were its wings strong enough, and could it land safely? To cut a long story short, those second two I didn't think were particular constraints for reasons we don't have time to go into today, and that getting into the air was the big issue for pterosaurs. So how did they take off? Well, back in the 70s, Bramwell and Whitfield did one of the seminal papers on pterosaur biomechanics. They suggested that they lived on cliffs and just sort of this is like the equivalent to the trees down theory, that they leapt off a cliff. Or they did some sort of running jump, but they were a bit vague about it, really. But that was the idea, that you lived on a cliff. Much more recently, Mike Habib and Julia Molnar and others have come up with this idea of a quadrupedal launch. It's based on the way that the vampire bats get into the air. So there's an analog in existing creatures, and the idea is that the forelimbs act as to push the creature into the air, and it sort of pole vaults over its forelimbs. So there you see the launch stance, and there's a sequence here that James Brown did for me of a Quetz taking off. So there it's standing there, it crouches down and then starts to push up with its forelimbs. It pushes up really hard and forwards as well, and its hind limbs push it forward, at which point it's into the air, and away it goes. And this, if I can get it to run, is another version more or less of the same thing. So here's our pterosaur, crouches down, crouches right the way down, pushes forward with its hind limbs, pushes up hard with the forelimbs, and launches away. So that's what's called the quadrupedal launch theory, and it gets you into the air. The important thing about that is that you end up using the same muscles for takeoff as for flight. And this is important because if you're a bird, you have separate muscles in your, obviously in your legs and your wings. So once you're in the air, your legs are useless. They're just mass that you don't need. So, you know, if you like, a bird would be better off without its legs once it's in the air, because it's completely separated the two functions. So every bird is a compromise between muscles for its wings and muscles for its legs. If you're a pterosaur, you combine the two functions. So you're using the same engine, if you like, for takeoff as for flight. So pterosaurs are not birds, and actually most bird analogies for pterosaurs don't work well. So just coming now to the end of things, what are the pterosaurs' advantages? Well, they have a low-speed flight capability. I didn't go into it, but that membrane wing allows them to vary the camber of the wing so that they can actually have a high camber wing at low speeds, which helps them to generate sufficient lift to fly slowly so they don't hurt themselves when they're landing. Most importantly, the forelimb muscle is used for launch and for flight. And also, you probably could see from that video of the Anangura crouching down, it has a very long stroke, because if you think back to the pictures for earls of the area, the green area, it isn't just a matter of how hard you can push, but for how long you can push. And that's to do with the length of your legs. So in the case of a pterosaur, because you're using your forelimbs, you have a very long stroke. So you have a powerful force, and that force can apply for a long period of time to get you into the air. Mike Habib and I did a whole lot of calculations on this, and looked and took those principles and applied them to a range of pterosaur sizes. And we concluded that the flight power is a weak constraint. You can get very big and you still would be able to fly. Your bones would start to get disproportionately large, but they don't affect the aerodynamics too much. Landing and takeoff are the more onerous conditions. Because of the ability to vary camber, a pterosaur can actually have a lower landing speed than some big birds. So that is potentially not an issue for limiting size, that you don't break things as you come into land, which leaves you with takeoff. And what we found was when you start looking at the scaling of takeoff and the launch stroke, it's highly allometric. In other words, it's as you get bigger, size works against you very strongly. And taking all that into account and taking the effect of the quadrupedal launch, our view is that the maximum size the pterosaurs could get to was somewhere between 9 meters and 11 meters wingspan. Certainly not more than 11. So much bigger than birds, probably about 200 kilos, 250 kilos. And so Quetzalcoatlus, we would argue, certainly wasn't flightless. So can they fly? Yeah, no problem. So thank you for your time. Let's see if there's any questions.
Well, thanks very